everyone. Today I wanted to start talking about YODA. So the title of this paper is YODA Enabling Computationally Intensive Contracts on Blockchains with Byzantine and Selfish Nodes. So I'm a co-author of this paper, and the first author is Saurav Das. Me and another student, Abhijit Anand. So these were two BTech students at IIT Delhi when I was there, and part of this work they did for their BTech project. So you can also be ambitious, those of you who are doing BTech and MTech projects, because this paper appeared in a top tier venue, NDSS 2019. Okay. So this attacked the same problem that TrueBit was trying to solve, but we saw that TrueBit was quite complicated and it didn't work when you had Byzantine adversaries. So of course it was assuming that everybody is rational, and it became very complicated. What if the task giver is malicious, and what if he colludes with the, let's say, the solver, of the solver colludes with the challenger, what happens, and so on. So this makes it more simple, and we also give a lot of results for that in fact it will work under certain conditions. Okay. So a high level picture of what we do is here. I'll just describe it. So in TrueBit we said that you can have any number of challengers and so on, right? I mean, anybody who is willing to put a deposit, of course, can become a challenger, and you could have lots of these. There was no strict upper bound on how many there could be, right? So anyway, so what we do here is that we say that we have initially we create something called a stake pool, where anybody can initially deposit some amount and become part of. And let's say that the stake pool remains steady for a long period of time. Okay, once in a large amount of time we can update the stake pool and allow people to withdraw their deposits and leave the stake pool, and new people to join. Let's say anyone can join at, let's say t equal to 0 or whatever, right, by depositing an amount. And then of course you have the miners. So the miners are going to do proof of work, plus they are going to execute non-CITs. So if there are many transactions in a block, all of them don't have to be CITs. Okay? And in that case, these miners would execute the other transactions. But of course these CITs would be specially handled by the stake pool. Okay. So here it's a little bit different from TrueBit. So TrueBit said ideally we want one person to solve, and that's the end of it. right? But of course, there was a question, how do you know he's doing it correctly? And so then we had to allow for challengers and so on, right? And that became a little bit tricky, because then too many people might challenge, and then how do you decide whether, when there is a challenge, about who's right and wrong? Okay. So of course, I'll explain in a moment what we try to do, but we have two threat models. So in the first threat model, we say that the stake pool has some fraction of Byzantine nodes. So it has Byzantine and honest nodes. And we are going to say that so the maximum, so we say that let's say that the fraction of Byzantine nodes is F. Right, and we don't know what this F is, but we are going to put an upper bound. And we say that this upper bound is some number less than 0.5. Okay, so it's sort of like we are preventing a 50% attack. I mean, if more than 50% of these stake pool owners are Byzantine, then we can't do much. Our method is not going to work. But if at least 50% are honest, it's going to work fine. Okay. And we have another threat model, which we'll discuss maybe in the next class or the class after that. So we'll go into how we deal with this threat model a bit later, but here the stake pool has Byzantine and rational nodes. So what is a node? Well, anybody who pays a deposit and joins the stake pool is a node. Right? And we are saying that here there is a combination of Byzantine and rational nodes, and this is a very powerful model because this is more realistic. Most of the literature you will find on blockchain security considers Byzantine and honest nodes. And it says that some people are totally malicious, they don't mind losing all their money or whatever, right? That is actually unrealistic itself, because unless it's a government or somebody who doesn't mind throwing away money, right? Because government's money is not their own, right? It's taxpayers' money. Right? But if you are spending your own money, normally you wouldn't be completely Byzantine, that you just be willing to throw away your money. It's more likely that you're going to be rational and you're going to say that what should I do to maximize my earnings? So this is more realistic, and it's one of the shortcomings of a lot of the work done in blockchain security research, okay, that we ignore this rationality. So this we'll consider later, but initially we'll just handle the first threat model. Okay. So suppose we had the first threat model, let's think what could we do. So suppose we are given that less than 50% are Byzantine, and let's say there is a particular CIT which has to be computing. And of course we are going to make assumptions like TrueBit also, that the CITs are pretty much independent of each other. You could have let's say two different CITs even running in parallel, but they don't update the same smart contracts, right? we're going to assume those things. I'll just write that here. So they don't have any dependencies between them. Okay? Or in fact, they don't have any dependencies on these 9 non-CIT transactions. So, but let's think for a moment, how would you deal with this? Suppose you knew that less than 50% of these were Byzantine, and you wanted a correct computation of a CIT. So the naive solution would be is to hand over this CIT to all the nodes and see what they submit, right? And then all that we have to do is look at the majority solution, and that gives us the right answer. So the naive solution is the following. Make all the stake pool nodes compute a CIT and take majority solution as the answer. So what could happen is, so suppose this is the, I'm plotting here the hash of the solution. Which is going to be some number, right? And here I am plotting a histogram. So the height is the number of nodes submitting this hash. Okay. So let's say this is S1, this is the solution that is submitted. Now the attacker, he could submit many other solutions, right? Suppose he submits S2, S3 and so on. Yeah. But we know that majority of the nodes are honest, so we can just look at this largest one and that gives us the solution. So this is good. I mean, we didn't have to do all the business of challenging and so on. Everything was straightforward, right? We just told everybody in the stake pool to do the computation, and told let's say all of them to submit the solutions to the blockchain as transactions, and we just found the solution straight away. Okay. So there's none of this business of the miners trying to decide, having some binary search and so on, like in TrueBit, to find out who's submitting the correct solution, right? But of course, there are some shortcomings. So one is that the number of solutions submitted is large. Okay. So in TrueBit, in theory, I mean, normally if everybody is honest, let's say, then you just have one solver, so he just submits one solution, right? So you're not using up space on the blockchain. Whereas here, let's say if you have 10,000 people in the stake pool, you get 10,000 answers. So for each CIT, you would have 10,000 transactions in the blockchain, which seems an overkill. Right? So number of solutions submitted is large, and assuming that let's say each stake pool node can run once, or let's say a limited number of CITs at one time. So let's say assuming each node can execute, let's say, m CITs simultaneously, the number of simultaneous CITs which can be executed is at most m. Right? Since everybody is running all CITs, we have at most m CITs running. So this solution is naive, and obviously this solution is not getting us a research paper, right? So what we want to do is we want to choose a subset from this stake pool to run the CIT. And then the question is, what could go wrong, right? Can we just look at the maximum now? I mean, look at this peak in the histogram of solutions submitted, right? And see whichever one has been submitted the most, and can we say that that is the solution, okay? And that turns out to be non-trivial to do. Let's try an alternative solution to the naive one. So suppose this is the stake pool. What we are going to choose is a subset of the nodes. So suppose the subset is something like this. Only this subset is going to execute the CIT, and only these nodes are going to put the result on the blockchain. So we call this the execution set. So we are moving a little bit closer towards TrueBit. So TrueBit of course wanted only one node to execute it. So here we choose a subset, okay? And we are not going to have challengers or anything like that, right? So we are just going to choose a subset, and only these nodes are going to submit the result on the blockchain. So the question is, how large should this subset be? Okay, so we said that in the overall stake pool, we are assuming that the Byzantine nodes are less than fraction f max. Okay? But what about in this set? So this is going to be randomly chosen. Can we again take the maximum? So again, let's say that within these nodes in the execution set, let's say that one solution, let's say this is solution 1 and this was the solution 2, and these are the number of nodes submitting S2, right? This is the number submitting S1. So can we say that S2 is the solution? So we could do this if the execution set was the entire stake pool, but the question is, can we do it here? And it turns out that we can't always do this because we are choosing a random subset, so there is a very small probability that even all the nodes may be Byzantine in this subset which we choose. Right? That may be very rare, right? So there is no guarantee that this peak that we choose over here is going to give us the correct solution. So there is no guarantee that this is correct. So what can we do with this this particular method of solving the problem? We've avoided submitting lots of solutions, so we said we'll choose a subset, but now we have a problem. There's no guarantee that this will give us the right answer. But maybe what we can do is we can just ensure that the probability of our choosing the wrong solution is very small. Okay, so suppose we ensure that the probability of the wrong solution is less than some beta. This is user specified. So for example, suppose beta is 10 to the power of minus 20. Okay, so this is a very small number. So with a very small probability, maybe we get the wrong result if we choose the solution which has the most number of votes. Okay? The number of nodes saying that S2 is the solution. Right? So suppose this is the case, we specify beta to be really small, and let's say that the size of the stake pool is 1600, and suppose we are given, we say that F max we are assuming to be 0.35, so not more than 35% are Byzantine. Okay. So what should ES be? So what should the size of ES be? So there are 1600 nodes overall. How big should the execution set be for us to guarantee that the maximum peak, the particular solution with the most number of votes is the correct one? Okay, with only the probability of error being 10 to the power of minus 20. And it turns out that this is going to be as high as 900. Okay. So it turns out that we have to choose a very large set, okay, in order to get the right answer, which is almost the same size, comparable to the stake pool. So this is one of the issues. So the ES for this particular choice, maybe for different choice, if F max is let's say 0.1, maybe we can do much better, right? Much smaller than this. So the execution set is very large. And secondly, there's another issue over here. So F max is the worst case. So we are designing the system for the worst case, something like 35% are Byzantine, but maybe in practice it is only 1% or 5%. And imagine if it was actually 5%. So suppose F was, so F is the actual fraction. So suppose F is actually equal to 0.05. Okay, so then how many nodes would we have to randomly choose in order to create this execution set? Probably a very few, maybe 10 nodes would have been enough. The probability that more than 5 nodes out of 10 randomly chosen ones is going to be Byzantine would be very small, right? And since we have designed it for the worst case, something like we have planned for this worst case, we had to choose 900, okay, which is really large. Okay, so if the actual fraction is much smaller than the maximum that we assume, then a much smaller execution set size would suffice. Okay. So what can we do? Can we choose a smaller set? Can we still get this 10 to the power of minus 20? Okay, but can we choose a smaller set? Okay, so it sort of seems impossible. if we are choosing one ES. But what if we allow many execution sets to be chosen? Okay, so here's what we're going to do in YODA. What we're going to do is we are initially going to choose one execution set which is very small, right? And if one of the solutions is overwhelmingly chosen by all of them, then that's probably going to be the right one. Okay. But if, for example, like shown in this figure, the number of votes for S1 and S2, let's say, are comparable, then we are not sure which one is correct, right? And so then we call for another execution set, okay? And we do this till we build up enough confidence about which solution is the correct one. Okay, so that's the idea of YODA, and let me describe that in some detail. So YODA has two main algorithms, and one of them is called Miracle. So YODA's Miracle algorithm. So what does Miracle stand for? Multi-round so we are creating an acronym from these letters: multi-round adaptive consensus using likelihood estimation. So what is the idea here? Well, we choose a small ES. So suppose we had the numbers we had earlier to, 1600 and Fmax 0.35. So I'll just give you the idea. So suppose let's write here. So I'll just give you a high level idea. Suppose Fmax is 0.5, SP is 1600. Sorry, not 0.5. Let's say it is 0.35. And let's say that F is equal to Fmax. It's a bad case, but suppose that is the true. What we are going to do is we are going to choose ES. Suppose ES is equal to 40, which is much smaller than 900. What may happen is that a fairly large fraction of this execution set is Byzantine, but of course some of them will also be honest, right? And suppose all the Byzantine people are, let's say, voting for S1. S1 is the wrong solution, let's say, and S2 is the correct one. So it may happen that S2 gets this many votes and S1 gets a little bit more. So here the number of Byzantine nodes are greater than the honest one, but not by a huge amount. Okay? So here we are not confident. So what are we going to do here? We ask for another set. Let's say that I won't write this as A and B and so on. Let me call it round 1. So we'll call for another round. And let's say we choose the execution set again to be 40. So this should be the size. So the fine details about how we choose the nodes and exactly how we do the mathematics to find which is the optimal, which is the best of these, so on, we'll look at a little bit later. But now I'm giving you the high level picture. So now let's say that the votes, maybe this time there are more honest nodes. So let's say that S2 gets more votes and S1 gets fewer. Right? So now we have more confidence but not enough. So we think that S2 is probably the right one, but we are not completely sure because we said with very high probability we should be able to guess the correct answer. And let's say we go on and we collect the data from multiple rounds, let's say round n. And again, let's say there are very few Byzantine nodes. Let's say most of the time in most of these rounds S2 was winning. So we are very confident and we say that this is the right solution. And so we stop. Okay, so it's a trade-off over here. So f is actually equal to f max and we chose this execution set to be small, so we had to go through many rounds, right, until we were confident and we saw which one is the right solution. So let's look at the case when f is much smaller. Let's say that f is equal to 0.1, let's say, right? And let's say that the size of SP is 1600. So let's say again we choose ES is equal to 40. So the thing is, we don't know what f is. We are designing for a worst case in this miracle algorithm, but we don't know what f is. So we don't know a priori. So we are designing and we are guaranteeing that even in the worst case of f is equal to f max, we are going to get, with probability 1 minus beta, we are going to get the correct answer. Okay? But what happens if f is much smaller? What is going to happen is that even in the first round, we might see S2 getting a large number of votes. And in round 2, let's say again, S1 is really has very few votes, S2 gets tons of votes. So here we are, let's say, almost confident. And here we are confident. Let's say with probability 1 minus beta that S2 is the solution. So we stop over here after the second round. So this is how miracle works. In case f is equal to f max, we may have to go through many rounds and we don't know exactly when we are going to stop. We're going to use some probabilistic technique to to decide when we are really confident and then stop. So this could take a large number of rounds, and we can design for how large these number of rounds are going to be in some expected sense, right? We can say the expected value for n, I want to be, let's say, 5 rounds. Okay, so then once I am given this expected value of n, automatically we get the size of ES. So given the expected number of rounds to stop, we can choose size of ES appropriately. And what is the advantage of this miracle algorithm? But that if f is much less than f max, we terminate much earlier. Okay, so this is assuming f is equal to f max, right? And here we actually terminate much faster. So let's say we've designed for 5 rounds in the worst case, but if f is much smaller, let's say 0.1, we may terminate in 1 or 2 rounds, okay, with very high probability. So this is why we call miracle adaptive. So it is adaptive to the value of f. We don't know what f is. If it's the worst case, then we take a certain number of rounds, but if f is much smaller, we terminate faster. Okay, and we get away with a much smaller set. Okay, so for example, here we chose 80 nodes to do the computation, whereas if we had gone by this other solution where we just chose a single execution set, then we would have needed something like 900, right? And even if f was much smaller. So it's a clever statistical method, okay? And it turns out that once when I spoke about this to the other faculty members, one of the professors in the AI group actually latched onto the idea, right? He realized that this is used in this particular setting, but it comes up in other problems in AI too, where you have some probability distribution and you're trying to find the peak of that particular distribution, right? So it turned out that this idea was useful there too. So in fact, along with me and my students, that professor has actually come up with even other methods which even outperform this particular miracle algorithm, right, in different settings. Okay, or at least they are more powerful. So for example, here we need to know f max and we design based on that. But using those other techniques, even if you don't know f max, you can design so that you do well.